Hello dear students, welcome to excellent series of lectures where we are learning the organic chemistry course with respect to boards, JEE as well as NEET. Well, before we start, firstly I'm hoping that you all are doing great. Excellent. So guys, this is Sagar Darvi, your chemistry teacher, and I welcome you to this excellent series of lectures where, let me tell you, prior to this we have studied a chapter called as haloalkanes and haloarenes, so which also included the reaction mechanism of that particular chapter, and we have learned that chapter in detail with respect to all the competitive aspects as well. So today I welcome you to the brand new chapter, that is alcohol, phenols and ethers. So guys, let me just show you what are our today's learning objective for this class. So you all can see on your screen, today we'll be first getting introduced to alcohol, phenols and ether. Of course, we'll see the general structures, how do we represent them. We'll learn about their classification, and wherever required, we'll also learn about a bit of nomenclatures of those particular compounds. Well, once that is done, we'll be straight away entering into methods of preparation of alcohols. So for today, we'll be starting with methods of preparation of alcohols. So in those methods of preparation of alcohol, we'll be learning three very important reactions. The first one would be by acid catalyzed hydration of an alkene, which you also call it as ACH. So we simply abbreviate it as ACH, that is acid catalyzed hydration. Well, you can see the next two reactions are also from an alkene. The second one will be by Oxymercuration-Demercuration of alkene. At times we also refer this as OMDM. Again, these are the abbreviation which we use for our convenience. Oxymercuration-Demercuration. And then finally, we'll be learning about Hydroboration-Oxidation of an alkene, which is also known as HBO. Guys, these are very interesting reactions, and it is always recommended that these three reactions must be studied together. And why I'm saying so, you'll understand that when we learn the details mechanism of these three reactions. As of now, let's get started with the introduction part of alcohol, phenols and ethers. Well, guys, before you read this, I want you guys to look at the simple reactions. If you look at the starting compound, we have got an alkane. And just imagine, visualize that from an alkane, I'm going to carry out substitution reactions such that one hydrogen atom is substituted by the hydroxyl group, hypothetically. So when hydrogen atom of an alkane is substituted by hydroxyl group, we get an oxygen containing compound where the OH group is directly connected to the carbon of aliphatic hydrocarbon. Such compound where hydroxyl group is directly connected to the carbon of aliphatic hydrocarbon, we call it as an alcohol. Now similarly, imagine we have got a benzene, right? Benzene C6H5, we can also represent it as PHH, just for the sake of highlighting one of the hydrogen atom. And I'm allowing this benzene to undergo a substitution reaction once again, where one hydrogen atom we are substituting with one hydroxyl group. If we do that, you will find the hydroxyl group, that is oxygen of hydroxyl group, will be directly connected to the sp2 hybridized carbon atom of benzene, that is aromatic hydrocarbon. So when hydroxyl group is directly connected to the sp2 hybridized carbon of a benzene, such compound we call it as phenol. This phenol very commonly also known as carbolic acid. So this is also oxygen containing compound where hydroxyl group is directly connected to the sp2 hybridized carbon atom of benzene. We call this as phenol. Now similar to this, when you talk about an ether, imagine we have got an alkane and we are now going to substitute this hydrogen atom of an alkane with the alkoxy group or aryl oxy group. Aryl oxy where oxygen is connected to aryl group. In both the cases, when hydrogen will be substituted by either alkoxy or aryl oxy group, we get a compound where oxygen is directly connected to the sp3 hybridized carbon atom of, let's say, aliphatic hydrocarbon, resulting in the formation of organic compound represented as ROR. So such kind of compound is known as an ether. Now this is an ether where both the valencies satisfying this divalent oxygen are alkyl, In this case, one of the valency is satisfied by the aryl group. So both can be considered as an ether. So guys, in general, when you look at, there's three class of compounds: alcohols, phenols, and ethers. One common thing we observe as far as their structure is concerned is that they contain oxygen atom in it. Hence, such organic compounds containing oxygen atom can be collectively also called as oxygen containing organic compounds. So alcohols, phenols, and ethers are nothing but oxygen containing organic compounds. Alright everyone, now let us start with alcohol and understand its classification. In the meanwhile, when we'll study several examples, we'll also try to assign IUPAC nomenclature to those compounds. So guys, as far as the classification of alcohol is concerned, well, there are several ways by which we can classify the alcohol. First, and the simple classification would be, in a given molecule of alcohol, how many hydroxyl group do you see? If you find an alcohol containing one hydroxyl group, we call it as monohydric alcohol. And if an alcohol is such which has more than one hydroxyl group in a molecule, then we call it as polyhydric alcohol. Just to understand that, let's have a look at some more example. So classification of an alcohol. First classification is based on the number of OH groups present in a molecule. The first one here is monohydric alcohol. If you look at all these examples, you have got N-propyl alcohol just carrying one OH. Here we have got isobutyl alcohol, again carrying just one OH in a molecule. And right here, tertiary butyl alcohol also contains just one hydroxyl group in a molecule. These all three compounds or the example are such where a molecule of alcohol is just containing one hydroxyl group. Such alcohols will be called as monohydric alcohol. On the other hand, if a molecule of alcohol contains more than one hydroxyl group, like 2 OH group, here also 2 OH group, here we have got 3 OHs, then such kind of alcohol will be referred as polyhydric alcohol. So simply, based on the number of OH groups present in a molecule of an alcohol, we classify them as monohydric and polyhydric alcohols. So dear students, let's try and understand the naming part of this. Well, now since we have taken the example which are all talking about an alcohol, so there is no other functional present, so you can call this as a monofunctional organic compound. In this monofunctional organic compound, because OH is the only functional group, that will be treated as a priority functional group. And priority functional group OH is such where functional group itself does not contain any carbon atom. So such functional groups are called as non-carbon containing functional group. Whenever you have any non-carbon containing functional group such as OH or NH2 or SO3H, so on and so forth, what we do is we look for that carbon atom of the longest chain where the OH is connected. So we have to make sure that the carbon atom to which OH is connected is becoming a part of a longest chain. Once that is done, then we identify that carbon atom which is directly connected to functional group OH, and we try and give lowest possible number to that carbon atom of the longest continuous chain of carbon. So because this is the carbon to which functional group OH is connected, this carbon firstly should be a part of longest chain, and now while numbering the carbon atom, this should receive the lowest possible number. So according to the numbering, I'll number it in this way. This says the name of compound will be total number of carbon 3, meaning word root will be prop. Because there is a carbon-carbon single bond, that is degree of unsaturation, so we'll use a primary suffix "ane", but you will see E of ANE is dropped because what is coming as a suffix alphabet is O. So the rule of IUPAC says when when the last alphabet of primary suffix like ANE and the first alphabet of secondary suffix which is O, if both are vowel, then one of the vowel, preferably the first alphabet of primary suffix, has to be dropped. The last alphabet of primary suffix has to be dropped, meaning we are going to drop this E from here, and that's how the name of molecule is propanol. Propanol, where since the OH is present at number 1, you call it as propan 1-ol, or you can also say 1-propanol. Have a look at this example, everyone. So OH is connected to this carbon atom, so we have to ensure that this carbon is a part of longest chain. So we selected longest continuous chain like this. So whatever is left is the substituent. So this is the substituent, which is methyl. I wrote alphabet next to that. Next rule says the numbering of carbon atom of all those carbon which are present in the longest continuous chain, and that carbon to which functional group is attached should receive the lowest possible number. So I'll number this as 1, this is 2, this is 3. So parent is again prop-ane-1-ol. But other than that, there is a methyl substituent at carbon number 2. So you will say 2-methyl propan-1-ol. 2-methyl propan-1-ol. That's the correct IUPAC name. Alright guys, now look at this. Functional group OH is connected to this carbon. So we have to ensure that this carbon is a part of longest continuous chain. So do not start your chain from here. Longest continuous chain meaning I can select this as a longest continuous chain. Or I could have also selected this as a longest chain, or I could have selected this as a longest chain. Anyways, once you have selected longest continuous chain, whatever else is left, what is left? This methyl is left, not a part of chain. We'll call this as substituent, which is a methyl substituent. Now, once you have selected the longest continuous chain, you have to ensure that the carbon carrying functional group receives the lowest possible number. So either you can go top to bottom or bottom to top. Anyways, functional group OH is getting attached to the carbon, which is number 2. Hence, numbering from top to bottom or bottom to top is going to give you same answer. And in that way of numbering, substituent is also receiving the same number. Again, total number of carbon in the parent chain are 3. So prop-N is your parent, propane. OH present at number 2. So propan-2-ol. Having methyl substituent also at number 2. So 2-methyl propan-2-ol is the correct IUPAC name of that particular compound. As we are just practicing the nomenclature, I am sure you have studied a separate chapter called as nomenclature. But as we mentioned, we are going to include everything that is required for boards as well. So ensuring that we are doing all the basics which are required for this particular chapter. Well, the next one is a polyhydric alcohol. Now I have got 2 OHs present here. So I'll select the longest continuous chain. See, this is non-carbon containing functional group. So to whichever carbon these functional groups are connected should be a part of longest chain. So that's our longest chain. And now the carbon to which OH is connected should receive the lowest possible number. So this is 1 and 2. Or you could have done it from right to left. So 2 carbon meaning eth. Carbon-carbon single bond meaning ane. And then I have got 2 OHs meaning it not just OL, it is diol. So now let me tell you, eth, carbon-carbon single bond ANE. Now E has to be retained because after E, that is ethane, we are going to get diol. The first alphabet is now D of a diol, which is the consonant. So I have to make sure that I am retaining this E. So ethane 1, 2 diol. Ethane, E is retained. Hyphen 1, 2 hyphen diol. Commonly also known as ethylene glycol. Alright, now here. This is functional group OH. Functional group OH. This is the carbon carrying first OH, carbon carrying one more OH. Both should be a part of longest chain. Once you have selected longest continuous chain, carbon carrying those functional should receive the lowest possible number. Meaning certainly in this case, I'll have to start numbering from right to left. So 1, 2 and 3. In this process, the largest number we are getting is 3. Meaning word root for the parent chain is prop. Carbon-carbon single bond ane. Right everyone? And now we have got diol, meaning E of propane has to be retained. But those diols are present at locus 1 and 2. So propane 1, 2 diol. Propane 1, 2 diol. Last example. 3 OHs, so trihydric alcohol, select the longest continuous chain such that the carbon containing OHs are the part of longest chain. And now the numbering of carbon atom is to be done in such a way that the carbon carrying OH receive the lowest possible number. Now any which is you do numbering, whether top to bottom or bottom to top, you're going to get the same numbering. So with this, now 3 carboning prop, carbon-carbon single bond ane, and triol, 3 OHs meaning triol at the locant 1, 2, 3. So you will say this is propane 1, 2, 3 triol. I'll write it down here. Propane, I am retaining E, 1, 2, 3 hyphen triol. Alright everyone. So that was classification number 1 on the basis of number of OH group present in the molecule, and in process we also revise the nomenclature part. Well, there is one more way by which we can classify the alcohols, which is on the basis of hybridized state of carbon atom to which OH is connected. For example, here let's say in this molecule OH is connected to sp3 hybridized carbon. So I will say this is the kind of alcohol where OH is connected to sp3 hybridized carbon atom. sp3 hybridized carbon atom. So such kind of compounds will belong to category of CsP3OH containing compound. You might find some alcohols where OH will be connected to sp2 hybridized carbon. So that is going to be CsP2OH containing compound, so on and so forth. So when you say OH is connected to sp3 hybridized carbon, there could be further sub-classification of that. That is, this is one example. Alkyl alcohol belongs to category of CsP3OH containing compounds. Similarly, you will also find a type of compound called as allylic alcohol, where OH will be connected to sp3 hybridized carbon only, but that is going to be a special allylic carbon. We are going to see that. And likewise, you might find benzylic alcohol as well. What I'm trying to tell you, let us see classification number 2 for monohydric alcohol based on the hybridized state of carbon atom. So the first category of compounds of alcohol containing sp3 hybridized carbon to which OH is connected. For examples here, OH is connected to sp3 hybridized carbon atom. You can see here OH is again connected to sp3 hybridized carbon atom. Here also OH connected to sp3 hybridized carbon atom. However, in the first case you will find OH is connected to sp3 hybridized carbon, which is directly connected to one other carbon. So the degree of this carbon atom is primary. So such alcohol will be regarded as primary alcohol. In the second example, again this is alkyl alcohol, isopropyl alcohol this is, right? But the OH is connected to sp3 hybridized carbon, which is a secondary carbon atom. So when function loop OH is connected to secondary carbon atom, we call it as secondary alcohol. In the third example, this is again sp3 hybridized carbon carrying OH, but the degree of that sp3 hybridized carbon to which OH is connected is tertiary. So we call it as tertiary alcohol. Simply, alkyl alcohol, that is ROH, alkyl alcohol certainly belong to category of sp3 hybridized carbon carrying OH. But further, depending upon the degree of carbon atom to which OH is connected, we further classify them as primary, secondary and tertiary alcohol. So the degree of alcohol decided on the basis of degree of carbon atom to which that function loop OH is connected. So that is the first type of alcohols containing CsP3OH. Now you will find again OH would be connected to sp3 hybridized carbon of allylic carbon. Now what is allylic carbon? Well, everybody see here. In this molecule, hold on everyone. Yes, if you observe carefully, OH is connected to sp3 hybridized carbon only, but this is the sp3 hybridized carbon which is directly connected to doubly bonded carbon or sp2 hybridized carbon. Such sp3 hybridized carbon which is connected to sp2 hybridized carbon is what we refer it as allylic carbon atom. So when the functional group OH is connected to allylic carbon, you call it as allyl alcohol. Further, such allyl alcohol can be classified into primary, secondary, tertiary allyl alcohol. How come? If this is allylic alcohol, if this is allylic carbon atom, find out its degree. Allylic carbon directly connected to only one carbon. So this is primary allylic carbon. So we call it as primary allyl alcohol. Primary allyl alcohol. Over here, look at the carbon atom to which OH is connected. Is it sp3? Yes, this is sp3 itself, but adjacent to sp2 hybridized carbon, which means this is certainly allylic carbon. But degree wise, this carbon connected to two other carbon atom directly, so this is secondary allylic alcohol. On the other hand, here OH is connected to sp3 hybridized carbon, which is adjacent to sp2, but such sp3 carbon is connected to three other carbon, 1, 2 and 3. So we'll call it as tertiary allylic alcohol. So basically, CsP3OH containing carbon could be adjacent to sp2 hybridized carbon, meaning they are called as allylic alcohol. And further, depending upon the degrees of those allylic carbon, we may have primary allyl alcohol, secondary allyl alcohol and tertiary allyl alcohol. Well guys, just as a practice, let's try to write down IUPAC names for this compound as well. Starting from here. Well, understand now you have got double bonded compounds along with the functional group containing OH. So we know the fact that functional group is always going to be our priority. Priority meaning we have to ensure that the carbon to which functional group is connected is a part of longest chain along with the double bond. Further, while numbering the carbon atom, because I have been saying that OH, functional group OH is our priority, I will ensure that the carbon to which functional group is connected should receive the lowest possible number. So this is 1, 2 and 3. So while writing the name, you will start with the word root 3 meaning prop. Now, degree of unsaturation, there is a double bond. So it is no more ane, it is ene. But that ene is present at locant 2. So prop 2 ene, and then I'm going to get ol. So since it is ene followed by ol, I have to drop the e of primary suffix ene. So it will be prop 2 n 1 ol. Prop 2 n 1 ol. Prop 2 n 1 ol. See, e have been dropped here. Let's see the another example. Okay. Now here, this is the carbon carrying functional group. So we have to ensure that carbon to which functional group is connected is a part of a longest chain. So don't stop here. You can still come down. That's a part of your longest chain. Now functional group is connected to the secondary carbon. So this should be receiving lowest possible number. So I'll start numbering from here. 1, 2, 3, 4. 4 meaning but. Double bond at 3. But 3n. And then ol present at 2. So but 3n 2 ol. But 3n 2 ol is the correct IUPAC name of this compound. And finally here, functional group OH is connected to this carbon. So this must be a part of longest chain along with the double bond. So from here, rather come down. If you come down, this methyl is not a part of longest chain. So we are going to treat it like a substituent. Right? And now, we want this carbon to receive lowest possible number. So I would rather start from this methylic carbon. 1, 2, 3 and 4. Well, now we know that substituent is to be written first. Right? So 2-methyl is our substituent. Keep it aside. You're going to start your name with 2-methyl. Then 4 meaning but. In present at 3. So but 3 n 2 ol. But 3n 2 ol, and prior to which 2-methyl. So the complete name is 2-methyl but 3n 2 ol. 2-methyl but 3n 2 ol is the correct IUPAC name. Well guys, so far in classification, first classification was on the basis of number of OH group present. We classified alcohol as monohydric alcohol and polyhydric alcohols. And now we started classification number 2 on the basis of hybridized state of carbon to which OH is connected. So we saw CsP3 OH containing compound. in which the further classification was allyl alcohol, primary, secondary, tertiary, and then we saw first one was alkyl alcohol, primary, secondary, tertiary, and just now we saw allylic alcohol, which are also further primary, secondary, and tertiary. Just like this, there exists another sp3 carbon containing OH, but when such sp3 carbon, you see here, this is sp3 hybridized carbon. When such sp3 carbon is directly connected to sp2 carbon of benzene, then such carbon is known as benzylic carbon. You call it as benzylic carbon. sp3 carbon directly connected to sp2 carbon of a normal aliphatic compound, you call it as allylic carbon. When such sp3 is connected to sp2 carbon of benzene, you call it as benzylic carbon. Here as well, you see sp3 carbon directly connected to sp2 carbon of benzene, so this is also benzylic carbon. You see sp3 carbon directly connected to sp2 carbon of benzene, so even this is benzylic alcohol. However, the degrees are different. Here the benzylic carbon connected to only one carbon directly, so this is primary benzylic. Here benzylic carbon directly connected to two other carbon, 1 and 2. So the degree of this carbon is secondary. So we refer this as secondary benzylic alcohol. Here benzylic carbon directly connected to three other carbon, 1, 2 and 3. So you call this as tertiary benzylic alcohols. So these were all cases where functional group OH was connected to sp3 hybridized carbon either of alkyl group or allyl group or benzylic group. And now we are going to talk about when functional group OH is connected to sp2 hybridized carbon atom directly. So alcohol compounds containing sp2 hybridized carbon carrying OH, right? Meaning OH will be now directly connected to sp2 hybridized carbon. Remember, when functional group OH is connected to sp2 hybridized carbon directly, such sp2 hybridized carbon is known as vinylic carbon atom. What do you call it? Vinylic carbon atom. So OH is connected to vinylic carbon, so you can also call it as vinylic alcohol. When such functional group OH is connected to again sp2 hybridized carbon of benzene, this is also vinylic carbon, right? But it is a part of a benzene, so this part will be considered as phenol. This is considered as phenol. You remember when we saw the introduction of alcohol, phenols and ether, when the OH group is directly connected to sp2 hybridized carbon of benzene, we call it as phenol. So this is certainly a phenol carrying methyl group at number 2, so you can say 2-methyl phenol. Alright everyone, so this was yet another classification on the basis of hybridized state of carbon to which OH is connected. So it can be a case of aliphatic or it can be a case of aromatic compounds such as phenol. So guys, that was about the introduction of alcohol, phenols and ethers, classification of alcohols, and just now we also saw in between the nomenclature of compounds. Well, once this is done, after alcohol we talk about a bit of an ethers. So as we saw, what are ethers? As far as representation of ethers are concerned, we write it like this, ROR. Instead of alkyl, you may have a aryl group as well. So ethers are oxygen containing organic compound where both the valencies of divalent oxygens are satisfied by either alkyl group or aryl group. Those alkyl and aryl may be same or may be different alkyl or aryl groups. Imagine if these two alkyl groups are identical in nature, then those kind of ethers are referred as simple or symmetrical ethers. And if the values of these two alkyl group or one alkyl and aryl group are present such that these two are different, you call them as mixed or unsymmetrical ether. So you can simply read this. If the alkyl or aryl groups attached to the divalent oxygen atoms are same, it is simple ether, and if the alkyl and aryl groups are different, it is called as mixed ether. For example, look at this. While naming this ether by the common system, we simply call them as dialkyl ether, meaning this is also alkyl, this is also alkyl, and both being identical, I'll call this as diethyl followed by the word ether. Diethyl ether. Imagine instead of ethyl, if I would have had two methyls, I would have called it as dimethyl ether. Imagine if I would have had both phenyl, I would have called it as diphenyl ether. So in case of symmetrical ether, by definition we know that both the alkyls or aryl groups are going to be identical. I can simply use term dialkyl followed by word ether in the common system of nomenclature. But imagine if you have got unsymmetrical ether where two alkyl groups are different, then find out alphabetically which is prioritized. So this is ethyl, alphabetically E. This is methyl, so it is M. Obviously, alphabetically, I am going to prefer ethyl. So you'll call it as ethyl, methyl, ether. Ethyl, methyl, ether. Alright everyone, that's how we talk about an ethers, and now we are talking about phenols. Like we mentioned in the introduction of this oxygen containing compound, phenols are the ones which are obtained by substituting one hydrogen atom of benzene by a hydroxyl group. So we say an oxygen containing organic compound where OH group, hydroxyl group, is directly connected to sp2 hybridized carbon of benzene, we call it as phenol. Now this phenol at times also referred as carbolic acid, do remember that. Okay, so you can see, ideally speaking, this should be phenol is the common name which is, or you can say a special name which is accepted as IUPAC name. So for every compound we are going to talk about their IUPAC name and also their common or special name accepted as IUPAC name. Okay, well, if you see here, other than methyl, rest is your normal phenol. So the carbon carrying phenolic OH is numbered as 1, this is 2. So as far as IUPAC is concerned, you can call it as 2-methyl phenol, 2-methyl phenol. However, with respect to its common name, we also refer this as methylated phenol. Why are we calling it as methylated phenol? Because in phenol, one of the hydrogen atom at the ortho position is substituted by a methylic group. Right everyone? I use term called as ortho position. In case if anyone is not aware of that, let me tell you. See, in this aromatic compound, this is the carbon where functional group is present, or for that matter some substituent is present. Any carbon which is adjacent to this carbon, meaning this or this, these positions are referred as ortho positions. Any carbon which is alternate to the carbon carrying functional group, this is the carbon carrying functional group, and alternate carbon to that is this, or even this. These carbons or these positions are referred as meta position. And any carbon which is opposite to the carbon carrying functional group. So this is the carbon carrying functional group and this is the opposite carbon in the benzene ring. This is called as para position. Very carefully, I'm making sure that the first alphabet is small letter here, ortho, meta and para. And the carbon atom to which substituent is present, the carbon atom to which the substituent is present, this position, sometime we refer it as ipso position. Ipso. Well, we won't need these terms. We are going to need ortho, meta and para other terms. So when you talk about ortho substituted compound or meta substituted compound or para substituted compound, very importantly, I want you guys to make a note of it. Ortho, meta or para terminologies are only used when your compound is disubstituted. In a benzene, there are overall 2 substituents. You are entitled to use term ortho, meta and para. But if you find any compound is having more than 2 or less than 2 substituent, you are not going to use that compound as ortho or meta as a terminology. For example here. Now, what is your priority functional group OH? So this is your priority carbon. With respect to this carbon, where is methyl present? At the adjacent position. So if this is the carbon of priority and methyl is a substituent which is present at the adjacent position. So adjacent position is called as what? Ortho. Meaning I can say methyl is present at ortho position with respect to the whole phenol. So you can call it as orthomethyl phenol. Orthomethyl phenol. But because methylated phenol are also known as cresol, C-R-E-S-O-L, I'm calling this as O-cresol, that is orthocresol. So see, I use term ortho because in benzene I've got altogether two substituents. One is OH, other is methyl. But what is your priority group? OH is the priority. So look at the carbon to which OH is present. With respect to this, where is methyl present? Adjacent position. What is adjacent? Ortho. Hence orthomethyl phenol or orthocresol. Keeping this fact in mind when you look at this, that's your phenol again. With respect to phenol, this is 1, 2 and 3. So IUPAC name will be 3-methyl phenol. That's 3-methyl phenol. Or methylated phenol are also known as cresol. But where is methyl present with respect to the carbon carrying OH? If this is carbon carrying OH, these two are adjacent position and this is alternate. Alternate meaning meta. Hence you are referring it as metacresol. Finally here, carbon carrying OH is this carbon of a priority. Fine. With respect to this, methyl is present at the opposite position, meaning it is at para position. So as far as ortho meta para terms are concerned, I will call this as paramethyl phenol or paracresol. And according to IUPAC, 1, 2, 3, 4. 4-methyl phenol. That's how guys you are calling them with respect to their common name and IUPAC name. Well, we have got some dihydric phenols as well. When two OHs are ortho to each other. When two OHs are ortho to each other directly connected to benzene, we can call this as catechol. So you can see its common name as a catechol. And according to IUPAC, benzene 1, 2 diol. When they are 1 and 3rd position to each other, benzene 1, 3 diol. When they are 1st and 4th to each other, benzene 1, 4 diol. Now, when two OH are adjacent, their common name is catechol. When they are alternate to each other, we call them as resorcinol. And when two OHs are opposite to each other, we call it as quinol or hydroquinone. Quinone or hydroquinone or quinol. These are the common name. Alright everyone. Well, other than this, there are some trihydric phenol also exist. Alright guys, I'll just give you introduction of those as well. Where should we write? Okay, I'll write it here. I'm writing some example of trihydric phenol, okay? So let's say if you have got 3 OHs adjacent to each other. Which you can also call it as benzene 1, 2, 3 triol. Of course, we'll come to the common name. Now, let's say I have a molecule where you see this is quinol, right? This is quinol, and I'm bringing one more OH in quinol, right? So you can say benzene 1, 2, 4 triol. And now if I put all the OHs alternate to each other, this is OH at first, OH at third, and OH at fifth. So benzene 1, 3, 5 triol this is. Okay. Now, as far as IUPAC is concerned, it's pretty simple. Benzene 1, 2, 3 triol, benzene 1, 2, 4 triol, benzene 1, 3, 5 triol. Now, as far as common names are concerned, well, this is what you call it as pyrogallol. Pyrogallol. Here, if I hide this hydroxy, the remaining structure is nothing but quinol. So in quinol, there is an additional hydroxy. So you can call it as hydroxyquinol. hydroxyquinol. And here, when the three OHs are alternate to each other, guys, we call this as fluoroglucinol. Glucinol. Alright, really not that important, but as we have studied dihydric, I thought of including trihydric compounds as well. So guys, that was all about the introduction of oxygen containing compound, their corresponding structures, how do we represent them, how do we classify them, and for some of those cases we have also talked about their nomenclature. And now we are all set to learn the methods of preparation. But let me tell you, out of alcohol, phenols and ethers, we are going to start with the first subtopic, that is alcohol. So starting with methods of preparation of, yes, first subtopic, that is alcohols. We're going to learn methods of preparation of alcohol today from alkene only. There are three reactions we are going to learn: ACH, acid catalyzed hydration; OMDM, oxymercuration-demercuration; and then HBO, hydroboration-oxidation. Well guys, we'll be starting this reaction soon. Give me a second. I want you guys to go through reaction till then. Well everyone, just have a look at the reaction. Okay guys, let's get started. The first method of preparation of alcohol from alkene is what you call it as by acid catalyzed hydration of an alkene. Okay. Well, I want you all to look at the reaction first, the general form of reaction. Okay, as you all can see, we have taken an alkene, and that alkene is allowed to react with water in presence of an acid. So when you say a water in presence of an acid, you can also consider this as a dilute acid. A dilute aqueous acid is allowed to react with an alkene, resulting in the formation of a secondary alcohol. Well, if you see the reactant and the product, what difference do you see? The pi bond has disappeared. Unsaturated compound became saturated, which means this is addition reaction. At the secondary carbon, I have got addition of OH, and the terminal carbon, number 1, which was CH2, has become CH3. CH3 meaning one hydrogen added here and one OH is added over here. So H and OH all together you have added water. That's how you can consider the reaction, right? Well, the first important thing which I want you guys to understand is, if you have studied a bit more of reaction, then there is a reaction which you are going to learn after this. In fact, in hydrocarbon, you study a reaction called as dehydration of alcohol. So if you see this reaction, this is more or less reverse of dehydration of alcohol only. Meaning if I take this compound and if I carry out dehydration, I'm going to get an alkene, right? And dehydration you carry out using an acid only. So that is also acid catalyzed dehydration. The difference in these two reactions lies is that because this reaction is equilibrium controlled, in case of dehydration of alcohol, we use concentrated form of an acid, whereas when we are carrying out hydration, look at the term, hydration is addition of water, so we are ensuring that water is taken in excess, and hence you will always find the reaction is carried out in dilute. When we carry out this reaction, ideally this reaction is carried out in presence of dilute aqueous sulfuric acid or phosphoric acid. These are two commonly used acids in presence of excess of water. Just a piece of information. You may not have any question on this, but just extra information for us. So this H plus that you see is from H2SO4 or H3PO4, but water is going to be in excess amount. All right. Now guys, how exactly does this conversion takes place? To understand that, let us see the reaction here. To understand, let us see the detailed mechanism here. Okay, so now if you see, we have got water. Okay, so let's take water here, which is in presence of an acid. So H plus indicate it is electron deficient. Lone pair on oxygen indicate it is electron rich. So it is very certain that the lone pair of oxygen will attack at H plus. So nucleophile is attacking at the electrophile, and that's how this will result in the formation of H3O plus with one lone pair intact. Right, everyone? Now this H3O plus, which is of course a source of H plus ion, will now be attacking at an alkene. So in the next step, alkene I'm taking here, R CH double bond CH2. Okay, and this is brought in contact with hydronium ion. I'm precisely mentioning hydronium ion. Now since hydronium ion is a source of H plus ion and alkene contains pi bond in it, we know the fact that alkenes, because of its pi bond, belongs to category of a pi bonded nucleophile. Pi bonded nucleophiles are the one which act like a nucleophile by attacking through its pi bond. Because pi bond is weaker, so it's a source of electron. So it's an electron rich species. Hence now this pi bond is going to attack at the H plus ion. Whereas if this pi bond is going to attack at H plus ion, obviously the pi bond will break towards one of the two atoms. Now recall what you learned in hydrohalogenation of alkene. Whenever pi bond attacks at electrophile, it breaks towards one of the two carbon such that the corresponding carbocation formed is stable. So this is primary carbon, this is secondary. So naturally the pi bond will break towards primary carbon, which makes it electron rich. That electron rich carbon will then accept H plus. So the sigma bond will go back on oxygen to neutralize the oxygen. But in this process, this carbon is losing this electron, hence going to become deficient, meaning this will be going to be a carbocationic carbon, and it is secondary carbocation which is going to be more stable than the corresponding primary. So what we got here is RCH plus RCH plus single bond CH2, which has now accepted H plus, right? And of course water has been set free, so plus minus H2, I'll write it down here. So guys, first important feature we realize here, because pi bond of alkene attacks at H plus. Firstly, since pi bond is attacking at H plus, or in other words H plus is attacking at the pi bond, it is electrophilic addition. So the reaction mechanism is electrophilic addition. This attack of H plus at the electrophile is found to be the slow step, resulting in the formation of carbocation. So one of the important feature of ACH is that it involves formation of carbocation. Now every time when we learn reaction mechanism, even in SN1 there was always a formation of carbocation. We always kept one important fact in mind, is that whenever there is possibility of carbocation formation, we always have to think of if there is any possible rearrangement. Because if any carbocation is formed which is not that stable but has a scope of becoming more stable carbocation via hydride shift, methyl shift or ring expansion, then those carbocation rearrangement always has to be considered. So we get here two important features. Number one, ACH involves formation of carbocation. If formation of carbocation is possible, then it may also undergo carbocation rearrangement, meaning carbocation rearrangement is possible. Now once you get carbocation, now water is all set to attack at this deficient carbon. So in step number 3, which I am writing it here, the carbocation which we have got R CH plus CH2H will be now attacked by water. So you can see here, water through its lone pair attacked at H plus, resulting in the formation of R CH carrying OH2 plus. CH2 H, and now this OH2H plus will undergo deprotonation with another water molecule. The water molecule will accept H plus, this bond will come back on O. So that's how the product I'm writing down here will be R CH. What I've got here is OH, and here CH2 and H. So guys, did we get the same product? Yes, we got the same product. Now if you see the overall addition, we had a carbon-carbon double bond to which OH and H got added. Now in OH and H, if you consider water which has H plus part and OH minus part, can I say OH minus part is the negative part of that reagent? Yes. So the negative part of the reagent OH is getting attached to that carbon which is more stable carbocationic carbon, or a carbon carrying lesser number of H. So this addition is in accordance with a Markovnikov addition. Hence, acid catalyzed hydration of alkene result in the formation of a product which is a Markovnikov addition, and hence I can also refer this reaction as a regioselective reaction. Well, I've explained what is regioselective. However, the other product form is so negligibly smaller, hence I'm referring it to be regioselective. So, in an alkene, OH, the negative part of the reagent got attached to carbon which was corresponding to the more stable carbocation, as you can see over here. Hence, I'll say this is Markovnikov addition. So guys, what all important features we have learned here? Number one, acid catalyzed hydration of alkene involves formation of carbocation. If it involves formation of carbocation, then there is always a possibility of rearrangement of carbocation. Second important point, reaction proceeds via Markovnikov addition. Other than this, some other important point which I discussed, one of that is whenever you carry out acid catalyzed hydration, we always use dilute aqueous H2SO4 or H3PO4. So important feature of this reaction are, it involves carbocation formation and hence rearrangement is possible. Second, it follows Markovnikov addition. Well guys, now let me show you some example, or rather a unique example of acid catalyzed hydration here, which is the only example that can produce primary alcohol. So let's say if you have got an ethene, okay, and upon arrow I'm mentioning that we have got, well, by the way, reaction is always an equilibrium controlled. Okay, so here H2O slash H plus. So dilute aqueous sulfuric acid, let's say we have taken. Well, since I've got only two carbon, addition of water across carbon-carbon double bond you can consider anyways. So let's say at the first carbon we added H, and at the second carbon got added OH. Now tell me, function loop OH has connected to that carbon atom which is directly connected to one of the carbon. So this is primary, which means the product here which we have got is primary alcohol. Guys, I want you all to think of, if you take any other alkene for that matter, well, just for the practice, I'm not going to write down the reaction. You take any other alkene, whether you take propene, Whether you take butene, whatever you want, whatever you want. Or you take isobutene, whatever. Let's say if you have got isobutene as well. And to this, if you're going to carry out addition of water, water is what? HOH. Since the important feature says it follows Markovnikov addition. So the negative part OH will always get connected to the carbon where the carbocation is more stable. So if this is primary and secondary, obviously carbocation here is going to be more stable. So OH will always attack here. Between these two carbon, primary and secondary, carbocation at secondary will be more stable. So OH will always attack here. In isobutene, now this is tertiary carbon. So carbocation is going to be more stable here. So OH will always attack over here. What does that indicate? In none of these cases, I can ever get a primary alcohol. Because if you have any non-terminal carbon atom in an alkene, that is always going to form a more stable carbocation. So the attack of OH will always take place at that substituted carbon atom or non-terminal carbon atom. Hence, other than ethene, you take any other alkene, you will always find the alcohol obtained is either secondary or tertiary alcohol. Which means ethene is a special case of an alkene where it is the only alkene which upon reaction with water, that is acid catalyzed hydration, will produce primary alcohol. No other alkene can produce primary alcohol. So remember as one information. Alright guys. Now since it is involving carbocation, imagine if I give you another example like this. What example should I give you? Okay. Let's say we have CH3, CH3, 3-methyl, 1-butene. Okay, that's the alkene given. And now you're carrying out acid catalyzed hydration. I'm directly writing now acid catalyzed hydration. So hydronium ion all set to release proton. So this is primary carbon, this is secondary carbon. So first you will break the pi bond such that relatively stable carbocation will be formed. So carbocation at secondary will be more stable. So primary is becoming electron rich, which is accepting H plus. Sigma bond will go back on O, right? So water will be eliminated. H will be attached to primary carbon, secondary will become carbocation. Well, so the carbocation would be CH3, CH and CH3 containing CH, single bond, CH3, CH2 and one more H. Now this is the carbocation. Well guys, now what is the degree of carbocation? It is secondary. Yeah. Now existing carbocation is secondary, but the adjacent carbon is higher degree than the degree of carbocation. I repeat, existing carbocation is secondary and adjacent carbon is higher degree than the existing carbocation. Whenever such case arises where the adjacent carbon is higher degree than the existing carbocation, it will always undergo rearrangement. Now because the adjacent carbon is tertiary, it will undergo hydride shift. So the entire H along with bond pair will shift from here and attack at the secondary carbon. When such rearrangement takes place, of course, we'll refer this as hydride shift. H minus shift, where you will now get CH3, CCH3, and now see this CH became CH2 because hydride attacked here, so this became CH2. This carbon became cationic and CH3. Well guys, now what is the degree of rearranged carbocation? The carbon which is carrying positive charge is 3 degree. So certainly tertiary carbocation is more stable than secondary carbocation. This was secondary carbocation. C plus, I'm symbolizing this C plus meaning as a carbocation. So this is tertiary carbocation, more stable. Because this is more stable, now the water can attack as a nucleophile. So water all set to attack here. water attacking here, followed by deprotonation. So what is effectively getting added? It's OH group which is getting added to this carbon. So if OH is added, you're going to get OH over here. CH3, CCH3, OH attacked here, followed by CH2 and CH3. So the product obtained is 2-methyl-butane-2-ol. Right, guys? So this is one of the example which we have considered which involve carbocation rearrangement. Well, to sum up this acid catalyzed hydration, acid catalyzed hydration is the process where we prepare an alcohol from an alkene by attack of water catalyzed by an acid. That's why we always take dilute acids. So generally you'll see dilute aqueous sulfuric acid or phosphoric acid would be taken. Reaction takes place in an equilibrium where the first step is electrophilic addition of H plus to the carbon-carbon double bond, resulting in the formation of a carbocation. So a few important features that we have to remember. Number one, this reactions involves formation of carbocation and hence rearrangement is possible like we did here. Second, the product of this reaction will always follows the Markovnikov addition and it's also regioselective reaction. Well, that is not so important. I want you to remember it is only ethene which can produce primary alcohol. Rest all alkene will always produce either secondary or just like here tertiary alcohols. Guys, that was all about ACH and now it's time for us to learn the second method of preparation, oxymercuration-demercuration. We also refer this reaction as OMDM. So as the name suggests, there are going to be two steps here. First one, oxymercuration, meaning addition of oxygen and mercury. Addition of oxygen will be in the form of water, that is in the form of effectively OH. And then you will be adding mercury as well in the step 1. In the second step, you will be removing the mercury. So we'll call this as demercuration. Okay. Let's see the general reaction here. We have got an alkene. Purposely we have taken unsymmetrical alkene to which we added mercuric acetate HgOAc twice in presence of tetrahydrofuran as the solvent, followed by water. Then whatever intermediate you get, you further treat that with sodium borohydride in an alkaline condition. Okay. Now let's understand the detailed mechanism because it is the mechanism which will make us understand how exactly the reaction is taking place. Firstly, we have mercuric acetate which I am representing like this. This is how structurally mercuric acetate look like. If you observe this part carefully, this part, it's a conjugate base of acetic acid. So this is acetate. Hence you're calling it as mercuric acetate. So in which this CH3CO part is a acyl group. Acyl group is also symbolized as AC, to which this oxygen is connected. So this can be also considered as OAC. So how many such OAC do you see? We have got 2 OACs. Hence, this is sometimes also referred as HgOAc twice. Alright guys, that's what basically it means. Now, this HgOAc undergoes autodissociation because acetate ions are a good living group. What are good living group, guys? You studied that in reaction mechanism. Poor bases are good living group. From where do we get poor bases? We get it from strong acids. So acetic acid is of course not as strong as mineral acid, but it is a good acid. So its conjugate base is poor. Poor bases are good living group. Being good living group, this is leaving. So what happened to Hg? An electron pair, but will be carrying positive charge because O has taken away this electron. And this OAC group is still intact. O, C double bond O, CH3. And another acetate left as a living group. O minus, C double bond O, CH3. Okay, so that's Hg plus OCOCH3. Well, once this is formed, now this Hg plus indicated is electrophilic in nature, and the alkene is your substrate, which we of course referring it as pi bonded nucleophile. So nucleophile will always have a tendency to attack at Hg plus. So pi bond will be attacking at the Hg plus. Now see what is happening here in step 2. I'm taking this alkene R CH double bond CH2, and what we have got here is Hg electron pair but electrophilic. Now this OCOCH3 I'm writing it as OSE for simplification. Now everyone, we know the fact that alkenes are pi bonded nucleophile. Being pi bonded nucleophile, they'll have a tendency to attack at electrophilic Hg. So for which pi bond will break, let's say, towards one of the carbon, making it electron rich, which will attack at Hg. In this process, this carbon is becoming deficient. When this becomes deficient, obviously we'll consider it to be becoming a carbocation. But before it could exist as a carbocation, or before it could be trapped as a carbocation in the reaction mixture, the electron pair of Hg attack at it, which means the scope of formation of carbocation or a scope of isolation of carbocation or trapping the carbocation is ruled out. So the first important distinction between oxymercuration-demercuration and ACH is, in case of ACH there was formation of carbocation, hence rearrangement was possible. Here there is no scope of formation of carbocation, so don't even think of rearranging the carbocation. So guys, HgOAC, now these all steps are taking place simultaneously. Which steps? Pi bond broke over primary carbon, attacked at Hg, immediately deficient carbon was attacked by the electron pair of Hg, and you get cyclic mercurinium type ion, which I am writing like this. R CH. Now double bond has become single bond. This is CH2 connected to Hg, formed a new bond. Now see, to neutralize this positive charge, electron was shared with it. So positive charge got neutralized, but again its own electron have been shared with others. So the positive charge is still intact here. So Hg plus and carrying OAC. Now what I want you all to look at is, look, Hg is carrying positive charge and this is 3-membered cyclic structure, which means naturally this ring structure will always be a strained ring structure, because 3-membered rings are always highly strained ring. So this ring would always want to open up. Now for opening of this ring structure, one of the two Hg bonds with the carbon has to be broken. So either this bond or this bond, which means both of this carbon are carrying partial positive charges here. And because you're carrying out reaction in presence of water, it is the water through its attack can open this cyclic ring structure. But attack of water at this deficient carbon cannot happen from the same side where Hg is present, because this side is blocked. So the attack of water will always take place from opposite side. Now when attack is taking place from opposite side, meaning from anti side, at which of the carbon the preferred attack will take place? That is answered by the attack of water, meaning a nucleophile, will take place at that carbon atom out of these two, which has more stable carbocationic character. There is no carbocation form, but the partial positive charges indicates that it has got carbocation type character. So whichever carbocation character is relatively more stabilized will be attacked by water. So naturally the carbon which is more substituted due to this plus I effect, this has a more stable carbocationic character. So this is the carbon which is resembling to stable carbocation. Hence attack of water taking place at this carbon, making this reaction regioselective when the reagent is selecting the attack of the region of attack. So it's a regioselective. So water will attack, followed by deprotonation. So guys, can I say the negative part? When deprotonation will take place, effectively who is attacking? OH. OH is attacking at that carbon which is more substituted. Isn't it Markovnikov? Yes, it is Markovnikov. So second important feature. First one was no carbocation formation, no rearrangement possible. And the attack of water in the cyclic or the bridge mercurium ion is following the Markovnikov addition. So water attacked here, and we've got R CH and OH containing CH2 Hg got back its electron pair and OAC. Right? Okay guys, just giving you a thought. Okay, imagine what if instead of water there would have been alcohol. Instead of water there would have been alcohol, meaning ROH. So O would have attacked and deprotonation would have taken place, meaning effectively instead of OH, OR would have got attacked here. Imagine if there would have been alcohol. So when alcohol's O would have attacked here, deprotonation would have taken place, and what would have been left attached to the carbon is RO. So what would have been that product? RO, and this whole can also be considered as alkyl group. So ROR is what? Ether. So the same process can be useful for the preparation of an ether, where instead of attack of hydroxy group, we'll show attack of alkoxy group. Hence, in that case, we are going to refer this reaction as Alkoxymercuration-Demercuration, because it is not hydroxy group attacking, it is alkoxy group attacking if we take alcohol in that case. Well, let's keep that aside for the timing. Once you get this, now in an alkaline condition, sodium borohydride is all set to attack. So sodium borohydride, NaBH4, in an alkaline condition. Well guys, the detailed mechanism step of this reaction is out of scope for our syllabus, so we are absolutely not going to discuss about what is the mechanism step. Simply you can consider for understanding is sodium borohydride is hydride donor, right? So let's say that H is going to replace this entire HgOAc. This is for understanding, not the mechanism. So if this HgOAc, if I replace it by H, the desired product is R CH, up here OH, and here CH2 and H. Once again we got formation of our desired product, alcohol, from a starting compound alkene. So across carbon-carbon double bond, you can see OH and H have been added, where OH, that is negative part, found to be attached to the carbon which is more substituted, and which means it indicates it is following Markovnikov addition. So two important feature of OMDM are it involves no carbocation formation, so no scope of rearrangement, and number two, the addition takes place via Markovnikov addition. So guys, up till here what has happened? You added mercury and you added oxygen. So this step is called as oxymercuration, addition of oxygen and mercury. And in the final step, mercury have been substituted, have been removed, hence you call it as demercuration. So that is oxymercuration-demercuration. Both the processes ACH and OMDM resulting in the formation of alcohol, where the overall regioselectivity indicate that it is following Markovnikov addition. However, in case of ACH there is always a carbocation formation, but in case of OMDM there is no formation of carbocation. So here are the important features. No carbocation formation, so we are not even talking about rearrangement, but it follows Markovnikov addition. Now guys, the same alkene which we took in case of ACH, imagine if we take it here. Same alkene. What was that? CH3 CH3 3-methyl 1-butene, right? Yes, 3-methyl 1-butene if you take it, and upon arrow if you see the reagent mentioned are number 1 HgOAc twice, along with water. Number 2 is reaction with sodium borohydride in an alkaline condition. First of all, the moment you see condition mentioned over here are oxymercuration and then demercuration. So identify that the reaction is OMDM. Once you do that, find out the important features of OMDM. What are the important features? There is no carbocation formation, so no question of rearrangement. And second, it follows Markovnikov addition. So now since I know that, I am going to add straight away water. So HOH. Because there is no rearrangement, I don't have to write down the mechanism at all. I just have to add water across carbon-carbon double bond such that the negative part will be attaching to the carbon which is carrying lesser number of H's. So OH will be attached here, H will be attached over here. So I can directly write down the product as CH3, CH, CH3. Now that is CH, carbon carrying less number of H. So since following Markovnikov, OH must be attached to this carbon, followed by CH2 carrying H. So that is your final product. That's how you're going to find out the product straight away. So you see how important features of these reactions are helpful to get the product quickly. Alright guys, and now finally moving forward with the last reaction for today's class, which is hydroboration-oxidation of alkenes. Well, firstly, for ACH, what was the reagent that we use? H2O/H plus, that is dilute aqueous sulfuric or phosphoric acid. But you will generally find H2O plus written, which means they're talking about ACH. Second, for oxymercuration-demercuration, NaBH, HgOAc twice, and water. And in the second condition, you will find sodium borohydride in an alkaline condition. Likewise, for hydroboration oxidation, the conditions will be B2S6, that is diborane, in tetrahydrofuran as a solvent, followed by oxidation step, which is using hydrogen peroxide in an alkaline condition. Okay, first of all, I want you to look at alkene and product and tell me, what do you think about addition? What is it following? I want you to think. Come on, everyone. Could you spot the difference in the product here as compared to the previous two products? Yes, the difference was here. The formation of alcohol is such where OH is connected to the carbon which is least substituted, meaning carbon carrying more number of H's. So it is contrary to the Markovnikov addition, meaning this reaction is following anti-Markovnikov addition reaction, which is absolutely correct. This is going to be one of the features. Now, how do we get this? Let us try and understand the mechanism. Well, guys, understand one thing. This B2H6, which means here this exists in a dimeric form, that is BH3 twice, dimer of borane, so you call it as diborane. So when we are talking about mechanism, okay, everyone, let's say we have got an alkene, propene we have taken. So to begin, first, of course, first step is hydroboration. You're going to add hydrogen and boron, and then you're going to carry out oxidation of whatever intermediate you get. Okay. So we are talking about step 1. Which is hydroboration. Okay. And now let's say we have got propene here. CH3, CH, double bond, CH2. Guys, let's call this is first equivalent of propene. Alright, first equivalent of propene this is, and to which addition of boron will be taking place. So just for understanding, I'm writing in a little different way, that is HBH2. Now look, what is happening here? If you talk about the reactivity of alkene with the boron, we know the fact, or we know the two properties of this two compound. One, alkene is a pi bonded nucleophile, so it is electron rich, whereas boron has sp2 hybridized boron atom, that indicates it has one vacant orbital. So due to presence of vacant orbital, this is going to act like a Lewis acid, meaning it is going to accept electron pair. Right? Boron is connected to 3 hydrogen, meaning 3 sigma bond. So sp2 hybridized, 1 p orbital is vacant. Because of that vacant orbital, it can accept electron pair from the carbon. So let's say pi bond broke over carbon, making it electron rich. That electron rich carbon then immediately attacked at the boron. This carbon became deficient, but before it could become carbocation, before it could be isolated as carbocation, this boron will release the entire hydride H minus, and that H minus will attack at this carbon. Now whatever we have shown, if I write down the 4-member transition state, it will look like this. CH3, CH, single bond, CH2. Now there is a bond formation between carbon and boron, and the pi bond is broken. So the bond which is broken, I am representing a partial bond. There is a new sigma bond in a process of formation with boron, carrying 2 hydrogen atoms. Now boron and hydrogen bond is in a process of breaking. So there is going to be a partial bonding between boron and hydrogen as well. And new sigma bond in a process of formation between hydrogen and carbon as a result of attack of a hydride on the carbon. So this is partial bond making. This is the 4-membered cyclic transition state. Because transition state is a state of highest energy content, it immediately decomposes to give you the product. So what product would it be? Whichever was supposed to break, we have to break that. So pi bond would be broken, so there will be single bond. Between carbon and boron, new bond will be formed, so there will be single bond here. This bond would be broken, so no bond between boron and hydrogen. And the new sigma bond between carbon and this hydrogen. So we will be getting CH3, CH, single bond, CH2 connected to BH2, and this is the new bond between carbon and hydrogen. Right everyone, so that's your step number 1, where we have added boron and hydrogen, rather hydrogen and boron, but hydrogen in the form of hydride and boron. So the step is known as hydroboration. Well guys, if you see the overall conversion over here, it appears like from boron, out of B and 3 H's, out of 3 H's, 1 H seems to be getting substituted by the entire alkyl group. See, you are seeing here BH2, meaning 1 H which was there have been substituted by this entire propenyl group, isn't it? We had a BH3, now in the product I can see BH2, meaning 1 H seems to be substituted by this entire group. So just like 1 H have been substituted by this entire group which was obtained from an alkene, there are 2 more H's which can also be substituted. So if 2 more H's can also be substituted, how many more alkene will we need? 2 more alkene. So this was first equivalent. We are going to need 2 more equivalents of the alkene. Now those 2 steps I'm writing down over here. Okay. And now we are not going to write down transition state. We will directly showing addition from here to the final. How? Let me show you that. Now let's talk about second equivalent. Okay. So second equivalent of propene is here. CH3 single bond, CH double bond, CH2 right? And now we have got this compound, because these two H's are going to get replaced by the propene molecule, right? So this molecule BH2, I'm highlighting one of the H and B, which is carrying one more H. So out of BH2, this is one H, this is second H, and the remaining is this propyl group, which is CH2, CHH, this is that CHH, and the methyl group. Okay, everyone. Now again carry out the same addition. What does the same addition means? Boron has vacant orbital, so pi bond will break. Carbon will become electron rich, which will attack at boron. This carbon becomes deficient, but before it becomes carbocation, hydride will attack here. All these things, all these three steps are going to take place simultaneously. So what are we going to get? See, starting with this CH3. CH3, single bond, CH, single bond, CH2, connected to boron, carrying one hydrogen, connected to, okay, hydride attached here. So this is that new H, and this is further connected to CH2, CHH. So this H which we are highlighting here, this one, is from the earlier or first H which was added from BH3. And this is CH3. Alright guys. So out of three H's, first H got added to the first alkene, or first H you can say got substituted. Then you left with only two H's. Now out of two H, again one more H got added here. Now see at boron how many H left? One more H left, meaning this H can also be added to the third equivalent of alkene. Hence, we'll be writing third step. So third equivalent. Okay, I'll write it here. Third equivalent. So propene, we have got CH3 single bond, CH double bond, CH2, and of this molecule, because this H has to be added to this carbon. So this BH bond I'm writing like this, B bonded to, okay, hold on guys. B bonded to hydrogen, and these two alkyl groups are identical. You see that? CH2 CH thrice, CH2 CH, CH2 CHH thrice. This is also the same, so I can write it collectively. CH2 CHH. This is whole twice, right everyone? And now you carry out the same step. Vacant orbital boron, pi bond will break, making this carbon electron rich. Rich carbon attacks at deficient boron. This carbon becomes deficient, but before carbocation could be formed, hydride. Hydride meaning H minus is attacking here. Now guys, one important step I want you guys to observe. See everywhere, here, here or here. The addition of boron and hydrogen is taking place from the same side of carbon-carbon double bond. Not to forget, in alkene, both the carbon atoms are sp2 hybridized. Both sp2 hybridized, meaning the geometry is going to be trigonal planar. Because this molecule is planar, and addition of hydrogen and boron is taking place from below the plane, meaning both have been added from the same side of plane, I will say this addition is syn addition. What is this addition? Syn addition. So wherever you see addition of boron and hydrogen taking place, you're going to call this as syn addition. Syn addition everywhere. Okay, well, so what is happening now? We will be getting a product. We're starting with this CH3, CH which got new H attached to it, single bond CH2, further connected to boron, which is further connected to this propyl group, which is present twice. CH2, CHH and CH3 present twice. So everyone, this is your N-propyl group. This is also N-propyl group present twice. So total 3 N-propyl group connected to boron. So we call this intermediate as trialkyl borane. What do you call? Trialkyl borane. Now this trialkyl borane is obtained after the first set of reagent reacting with 3 equivalents of propene. So you had 3 equivalent of propene. And now once this condition is producing trialkyl borane, we will further carry out oxidation. That's the second part. So hydroboration is done. Now what we're going to do? Oxidation. So let's see what happens in oxidation. Step number 2 is oxidation. Okay, so trialkyl borane is what we have got. Let me put that here, trialkyl borane. B. Okay. Connected to CH2, CHH and CH3. CH2, CHH and CH3. CH2, CHH and CH3. Well guys, there is a particular mechanism step here, but for us we don't need that. So we are directly writing how exactly are we supposed to understand the product formation. Let me write the conditions here. What are we using? We are using hydrogen peroxide. In an alkaline condition. Okay. So simply to understand, what you can do is, look, imagine if I break down this boron and carbon bond like this. And hydrogen peroxide that I've got, I'm putting it this way. OH, OH, just for the understanding, by the way. So you use one equivalent of hydrogen peroxide to break one boron carbon bond. This is for the understanding only. So OH group will be connected to CH2. Right, everyone? Similarly, do that here, second equivalent. So we have got OH and OH. And finally, third equivalent. OH and OH. So you can see every CH2 is going to get attached to OH. So CH3, CH2, CH2OH. Alcohol, CH3, CH2, CH2H. Second equivalent of alcohol, CH3, CH2, CH2H. Third equivalent of alcohol. And B carrying 3 OHs, OH, OH and OH. So we will be getting product 3 equivalents of CH3, CHH, CH3, CHH, and now CH2 carrying OH. Well guys, what we have seen here is not the mechanism, it's just for the sake of understanding. So now in this final product, if you observe, you will realize OH group is getting connected to that carbon which is least substituted or the one which is carrying more number of OH. So this is following the anti-Markovnikov addition. So overall, if you see the important features of this reaction, number 1, hydroboration step where addition of boron and hydrogen takes place from the same side of carbon-carbon double bond. So hydroboration is syn addition. Secondly, there is no formation of carbocation at all, so no scope of rearrangement. So hydroboration is syn addition, no carbocation formation, so no scope of rearrangement. And third one, it follows anti-Markovnikov addition to produce a final product. Alright guys, so that's how the reaction takes place. Well, again, the detailed mechanism step of oxidation is not required for us, so we are not writing it, although it exists and it is being traced properly by the mechanism, but we are not going to do that step here. So the key feature of hydroboration oxidation: hydroboration is syn addition. It involves no carbocation formation and it follows anti-Markovnikov addition, which means once again, if we have been given an alkene like we used for earlier too, we were taking 3-methyl-2-butene as our substrate, 3-methyl-2-butene. Methyl-2-butene, and upon arrow, if we see the condition mentioned are: number 1, B2H6 in tetrahydrofuran, followed by hydrogen peroxide in an alkaline condition. So what are we going to do? We'll observe the condition. Okay, so hydroboration. So this reaction is HBO. What are the key features of HBO? Hydroboration is syn addition. Second condition, no carbocation. No carbocation, and follows anti-Markovnikov addition. So now when you are adding water, simply identify the negative part in water. So OH is your negative part, that is going to get attached to the carbon carrying more number of H's, meaning less substituted carbon, and H will be added here. So straight away, because there is no rearrangement involved, I don't have to verify with the mechanism. Straight away I can say this is CH3, CH, CH3, CH2, and here it is CH2, OH. Alright guys, in case of OMDM, you would observe OH was connected to secondary carbon, right? See, OH was connected to secondary carbon. Here it is. And in case of ACH, because of rearrangement, OH got connected to tertiary carbon. So that's how these three are important reactions, and I would recommend you guys to always revise these reactions together because they are similar in pattern. The substrate is same alkene, the product is same alcohol, only set of reagents and the mode of mechanism is different. So just to conclude, everyone here, when we talk about the first reaction, which first reaction? Acid catalyzed hydration. Important feature of that acid catalyzed hydration is that it involves carbocation formation and hence rearrangement possible, and it always follow Markovnikov addition. Other than these two more important points, the reagent that we use is dilute aqueous sulfuric acid or phosphoric acid, and only ethene produces primary alcohol, rest all will produce secondary or tertiary alcohol depending upon the structure of alkene. Second, the second one which we carried out was OMDM, Oxymercuration-Demercuration. You know the sets of reagents, for which the first important feature is that it involves no carbocation formation and the product obtained is always via Markovnikov addition. So ACH and OMDM both Markovnikov addition. And third, hydroboration oxidation. First step, hydroboration is syn addition. It involves no carbocation formation, so no scope of rearrangement, but the final product is in accordance with anti-Markovnikov addition. Alright guys, well, that was all about our first class of alcohol, phenols and ethers, where we included introduction of this 3 oxygen containing compound, their classification and their nomenclature wherever required. Once that was done, we studied the methods of preparation of alcohol. The first subtopic we started, where we learned the methods of preparation of alcohol with respect to ACH, acid catalyzed hydration, OMDM, Oxymercuration-Demercuration, and HBO, that is hydroboration oxidation. So guys, that is it from our today's class. I'll see you soon in the next class with the further part of alcohol, some more methods of preparations and some chemical properties. That is it. Thank you so much everyone for attending the class. I'll see you soon. Bye bye. Take care.